Hello, class. In the previous module, we talked about the elements in the periodic table and how they are being arranged according to the number of protons that are present inside their nucleus. Now, you can tell the number of protons the element can have by looking at its atomic number. So, for instance, for sodium, it has an atomic number of 11, which implies that there are 11 positively charged protons that's located inside its nucleus. We can see that the difference for magnesium really is that magnesium has one proton more by looking at its atomic number, right? Now, for neutral atom, the number of electrons must equal to the number of protons. That's because electrons is negatively charged. It will cancel all the positively charged species, and that is your proton. So for sodium, if it has 11 protons inside the nucleus, then for a neutral sodium atom, it only implies that there's also 11 electrons surrounding the nucleus. Okay. Now, when we have one atom trying to react with another atom of either the same type or different kind of atom, the first interaction or the first contact is usually the ones in the outermost level. And these are usually the electrons that gets in contact with each other, not the protons, because the protons are located in the inner core, which is your nucleus. And so the positioning of these electrons is really vital in knowing the behavior of an atom, in knowing how they react with other elements um, in the world. So positioning of electrons is very important. Um, we're just going to focus on the first 20 because this is really a complicated topic and which is beyond the scope of our class. But the locations of these electrons are not just flying everywhere, okay? There are some location, assigned location that these electrons have prefers to be residing. And that's why we call this electron configuration, okay? Or otherwise known as the location or the address of these electrons, where they are residing. Now, you're going to see that there are two video YouTube clips that I have attached, and I encourage you guys to watch this. They have very good visual content, but at any rate, I'm just going to summarize the two contents here. Okay. If we focus on the 20 elements, the first 20 elements from hydrogen all the way to calcium, these elements, the electrons will basically, of the first element, hydrogen, versus the electrons in helium, which has 2 electrons. The location of these are very similar, okay? They just differ because the number of electrons increases over time. Now, they would reside, if you think about it, protons are positively charged, they're residing in the nucleus, and electrons are negatively charged. Electrons are surrounding the nucleus, and these electrons get attracted to the core of the atom where the protons are residing at. So the very first location, it's kind of like building a town. You want to reside or have a house closer to your work. And so you're going to start building a house close to your work until that spot is going to be very heavily populated, or the real estate price has really gone up. Then you have no choice but you look for other locations a little bit outskirt from, a little bit far from that area near to your work. So the same thing happens here when it comes to positioning the electrons in your atom. They would be attracted very close to the nucleus at first, but there's only a certain number of spots that you can fill in that location. So here I'm just going to show you 3 locations or 3 levels or orbitals. Okay, the first energy level can only occupy 2 electrons. The second energy level, which is in the a little bit farther from the inner core can only contain 8. So I'm going to put here 2 for the first energy level, 8 for the second energy level, and another 8 for the second energy level. The fourth energy level here can contain 2, but it can actually contain more, but we're just focusing here on the first 20, okay, elements. So 2 plus 8, that's 10, plus 8, 18, plus another 2, a total of 20 electrons. We're just focusing here for 20. Okay, so here I'm just highlighting 4 elements, okay? And I'm just showing you the electrons. So hydrogen has one proton, and also 1 electron for a neutral atom. And we're just focusing here on the electrons. So hydrogen has 1 electron, lithium has 3 electrons. The first 2 is located on the first energy level, and the last electron is located in the outer energy level, okay, or energy level 2. For beryllium, there's going to be 4 electrons. The first 2 is going to be located in that first innermost shell, and then the other 2 will be filled on the second shell. So once you filled up the first shell, which only has a maximum of 2, then you're going to start filling it on the second energy level. So if you look at sodium, sodium has 11 electrons. You're going to start filling the first 2 in the innermost, or the first energy level. So that's 2 electrons right there. It's already full. Then you move on to the next, the second energy level, and it can only occupy a maximum of 8. So 2 plus 8 is a total of 10 electrons, but sodium has 11. That means to say that the last electron of sodium will reside on the next energy level, and that's energy level 3. So if you count, that's 2 plus 8, 10 plus 1, that's a total of 11. Okay, I'm not showing here the dots, but you get the gist. You can fill the number of electrons here by dots, but I'm just writing it out to you so that you can see it. Now, as you get more and more electrons, if the bigger atom you are, you're going to get more and more electrons, then the more of these energy shells and dots you're going to draw, right? Which is very tedious and time consuming. So instead of doing that, we have this shorthand method of writing the positions of these electrons. We call that the shorthand method, electron configuration method. Okay, now there's also other methods here. If you're going to take a higher level of chemistry, you're going to do the really full electron configuration, or the shortcut, no, not shortcut, but the noble gas electron configuration, or the abbreviated noble electron configuration. And you're also going to be able to write the positions of these electrons in terms of the quantum mechanics electron configuration. We're not going to get to that. We're just going to use the shorthand electron configuration method. How does that work? We're going to write the electrons depending on the location. So for hydrogen, there's only 1 electron on the first energy level, so you're just going to write 1, and that's it. For lithium, the shorthand electron configuration will be 2.1. It implies that there's a total of 3 electrons in lithium. The first 2 is on the first energy level, and the last electron is on the second energy level. If you're asked to write the shorthand electron configuration of beryllium, it's going to be 2.2. You get the gist. For sodium, it's going to be 2.8.1. Okay, so if you add them all up, it should add up to the total number of electrons present in that atom. So that's one. I'm going to test you on how to write the shorthand electron configuration on these 20 elements. The second point that I want to highlight here is some trends. Okay, notice that for hydrogen, lithium, and sodium, these 3 elements are picked from group 1 column, okay, or the family group 1A. Now, notice the shorthand electron configuration and the last number there. It ends with the number 1, 1, 1, 1. They have 1 electron in its outermost shell. Okay, so notice how the trend there for these elements, and you can do and try for potassium. Notice that the last, the electron, the number of electrons in its outermost energy level will coincide to its group number. So for these elements, hydrogen, lithium, and sodium, the number of electron in its outermost energy level must be 1 because it's in group 1A. Try that for beryllium, magnesium, and calcium. You'll notice that the outermost level, electron in the outermost level will have or will contain 2 electrons. For elements here in group 3A, there's going to be 3 electrons in its outermost level. For groups 4, 5, 6, 7, and 8A, the outermost electron or the electrons in its outermost energy level will be 4, 5, 6, 7, and 8 respectively. So we call these electrons in the outermost shell valence electrons. Electrons in the outermost energy shell or energy level. Okay, and the number of electrons will coincide with the group number that this main group elements can be found. So if I'm going to ask you, what is the valence electron for oxygen? Since oxygen is found in group 6A, then you're going to say there's 6 electrons in its outermost level. How many electrons are present in oxygen, in neutral atom oxygen? You're going to say 8, 6 of which are in its outermost level. How many electrons are present in selenium? There's 34, but out of the 34, 6 of them are in its outermost energy level. Okay, I hope that makes sense. Okay, we could ask you that way, or another way of drawing, instead of focusing. Okay, let me pause for a bit. When you are asked to write the shorthand electron configuration method, or just the electron configuration method, you are focusing on all of the electrons and where they are positioned. So say for instance for sodium 2.8.1, you know that there are 11 electrons. 2 of them are located on the first energy level. The other 8 can be found on the second energy level, and the last one can be found on the third energy level. Okay, so we're focusing on all of these electrons and where they are being positioned. But like I said, when we're looking at the interaction of this atom with another atom, we're really looking at the electrons in the outermost shell, or the valence electron. And so we're just focusing on this one right here for sodium. Okay, so because of that, we're also sometimes going to be asked to draw the Lewis dot symbol for the element. So for the Lewis dot symbol, we're just going to write the symbol of the element. So for sodium, you're going to write sodium, and then you're going to write the number of valence electrons in a form of a dot. So for sodium, it belongs in group 1A. There's, out of the 11 electrons, 1 of its electron is located in this outermost shell. So you're going to write or draw it out as a dot. Okay, there you go. So beryllium has 2 valence electrons, so you do 2 dots. Okay. If the element has 3 electrons, and we write it up there, then you're going to write 1, 2, 3. It doesn't matter where you position it, as long as you just show there are 3 dots. For 4, you could write it as the fourth, as the second pair. 5, 6, 7, 8. Like I said, it doesn't matter where you're going to put these dots, as long as you arrange them in the order of either twos. So a pair, 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 pair. The maximum electrons that you can fill in the outermost energy level is actually 8. Okay. Now, here's the thing. Elements cannot be found, not all elements, there's rarely elements exist in nature by itself. Okay, you can never see a pure sodium in the kitchen. It's usually found in a compound. It's usually bonded to another element. Okay, that's because it's actually not very stable. So, um, or another way of thinking about it, a pure element is not stable in its own. Or another way of thinking about it is that elements are stable if they are being paired or bonded to with another element. Okay, we call this the octet rule. They discovered that the elements follow what we call as the octet rule, meaning to say, in order for them to be stable in nature, they need to have 8 electrons in its outermost shell. So take a look at neon, argon, krypton, helium. They all are in group 8A. They have 8 electrons in its outermost shell, except for helium. Helium is a small element. It can only have 2 electrons in its outermost shell, filled energy level. Okay, but they're pretty much 8 electrons in their outermost shell. They're very, very stable, and that's why these elements hardly react if there's another atom next to it. So these are called noble gas elements. They're very noble, royalty. They don't have any interaction as much, or any they don't react violently. Okay, now take a look at sodium. Sodium only has 1 electron in its outermost shell. Okay, in order for it to be stable, it has 2 choices. You can either find an external source that can donate 7 electrons in order to fill the 3rd energy level to its maximum capacity of 8, or you could get rid of that 1 electron, hence stripping the 3rd energy level and exposing the 2nd energy level and its contents, 8 electrons. Okay, so sodium has 2 choices, and in the next video, you're going to see the preference of sodium. It's very easy to get rid of that 1 electron and exposing that 2nd energy level and its 8 electrons. So when you have 8 electrons, you're going to be stable. Okay, so sodium there would rather give away its electrons. And just like all metals tend to give away its electron, hence exposing its inner shell and its 8 electrons inside. When you give away your electron, you're giving a negative charge. So you're going to have more positive in you. So if you give away 1 electron, now your sodium will now have 10 negatively charged species, or 10 electrons. And the protons didn't change because they're inside the nucleus, right? Look at the charge of sodium now. The sodium will now have a positive 1 charge. Okay, so neutral sodium will have 0 charge, but it's rarely found in its neutral form. It's not stable that way. It has 1 electron in its outermost shell. It's not stable. For it to be stable, it has to bind with another element. And in the binding process, it has to relinquish 1 of its electron away in order for it to have a positively 1 charge. The sodium is no longer neutral. Your sodium will now be a charged species, positive 1 charge. It's going to be ionized, but it's stable that way because now it will have 8 electrons. Okay, so then point here is that you can never see an electron in its neutral form, but rather you will see it in clumps. It's going to be binded to another element in order to form a compound, and it's very stable that way. If you want to get sodium in its purest form, you have to chemically react and separate it from the other element in order to get it in its purest form. Not very stable. The product you will get will be very pure, but it's not going to be stable. It's always going to go back and form into a compound form. So if you look at lithium, in order for it to be stable, you would rather give away its one electron than exposing its inner shell that is fully filled electron. Okay, so remember, lithium is one of those small elements that only has 3 electrons. So in order for it to be stable, it's just happy to have 2 electrons right there. So, and be like helium. Okay, so lithium, if they all will get rid of its one electron in its outermost shell, they will form an ion that will have a 1+ charge. For group 2 elements has 2 electrons in its outermost shell, and since they're metals, they would rather give away that 2 electrons in order to form an ion that has a 2+ charge. So most of the metals, once they become ionized, they give away and lose their electrons, they will form charges. And their preference is always getting rid of that electron in its outermost shell. So for group 1A, 2A, the ions that you will form will have 1+ charge and 2+ charge. For group 3, you will have a charge of 3+, if you're going to form an ion. Okay, if it's going to bind with another element in order to form a compound. So we're going to skip this 4 because 4 could either give away its electron or receive 4 electrons in order to form a stable element. Now take a look at the non-metal here, nitrogen. Okay, let me just find some space. Nitrogen has 7 electrons. The first 2 is located in the first energy level. Then we have 5 electrons in the second energy level, total of 7. So 1, 2, 3, 4, 5. Okay, 6, 7. Okay, so the shorthand electron configuration is 2.5. Of the 7 electrons, there's 5 electrons in its outermost shell. Okay, now in order for it to be stable or to have 8 electrons around its shell, it could either have 2 choices again. It could either find an external source that would accept its 5 electrons, hence exposing this filled stable energy level of 2, or find an external source that can supply 3 electrons in order for it to be stable. And I think finding an external source that will give or supply 3 electrons is easier than getting rid of those 5 electrons. Okay? By accepting 3 electrons, you will have a charge of 3-. And for oxygen, by accepting 2 electrons, 2 plus the 6 in its outermost shell, you're going to get 8. So that's 2 electrons. It's easier to do that. Fluorine has 7 electrons in its outermost shell. For it to find a supplier, an external source that can supply 1 electron is easier, hence obtaining a -1 charge. Okay, so these are the charge ions that will be formed from these elements once they pair up or react with another element. That way they will be stable. We're going to revisit this again when we're dealing with compounds. But just know that for a compound to be formed, especially an ionic compound to be formed, they will require ionized versions of these elements. And for you to know the charge of these ions, for metals, it just coincides with the group number. So for group 1A elements, the ion that you will form will be 1+. For group 2, it will be group 2+. For group 3, it will be 3+. But for the non-metals, the ions that you will form, because they would rather accept an electron from an external source, they will have a negative charge. So it will be the group number -8. So 5 minus 8, the charge will be 3 negative. For oxygen, sulfur, selenium, since they are in group 6A, if they become ionized, they will have a charge of 6 minus 8, so that's 2 minus. For halogen family, since they are group 7, 7 minus 8, the charge of these ionized elements will be 1 minus.